Okay, let's get started. So thank you very much for attending our 83rd NIA CFD Seminar. Presenter today is Hiro Nishikawa, and for that reason I'm going to skip introduction. And the topic today, co-authored actually both by Hiro and Ilyu, is recent kind of challenges in implementation of hyperbolic Navier-Stokes method for real applications that involve High-Reynolds-Number boundary layer flows.
Thank you. Thank you for coming. So this work is already published. It's a conference paper 2017 cited. And work with EU and funded by NASA. I want to talk about the greatest tip in healthy life. The greatest tip for healthier life is if you suffer from high blood pressure, cholesterol, sugar, lose weight, and you'll be healthy. And this is a great tip because it works and clinically proved by these papers. But this is not practical because the biggest question to many people is, okay, how do I reduce the weight? And that seems to be a very difficult question. And answer varies from person to person. And some approaches are not always intuitive. Eat breakfast, drink water, turn off TV. Looks like they work for some people. So it's not always intuitive. What's the greatest tip in CFD? It is if your CFD code doesn't work, add more artificial viscosity and it will work. This is the greatest tip because it works in many cases. And in this case here, this is I'll find upwind flux, but this is basically central flux plus dissipation. Or sometimes it is called artificial viscosity or penalty term or high frequency jumping. Just increase this term and it will work. But again, this is great, but it doesn't tell us exactly how and how much to add. If you add too much, you'll be in trouble too. And there are many approaches are there in CFD. Of course, artificial viscosity, you directly add viscous term with artificial coefficient or Riemann solvers. Riemann solvers are approach to introduce the right amount of dissipation. Artificial upwinding, large H contribution in the case of viscous term or compact viscous stencil to reduce high frequency errors. And this talk is about High-Reynolds-Number boundary layer flow. And for boundary layer flow in a model equation, it is well known that there is a mesh Reynolds number restriction. And that also has something to do with dissipation. I don't think this is well known. I will talk about that later. So the hyperbolic Navier-Stokes, this is the method we are trying to develop within Fun 3D. And we are solving large number of equations. Is a continuity, momentum, and energy. And we add equations for the velocity gradient, and heat flux, and density gradient. And then we introduce artificial mass diffusion. So these new variables, G, Q, R, are directly related to the gradient or the primitive value. So we call them gradient values. And there are two references published conference papers about these 3D hyperbolic Navier-Stokes. Basically, this approach is to derive a spatial discretization of the Navier-Stokes equation. Once you add these some pseudo-time evolution equations, this whole system now becomes hyperbolic in the pseudo-time. And you can find eigenvalues and eigenvectors, at least for the viscous part. And then you can construct upwind schemes. So it simplifies viscous discretizations and so on. You can apply anything you know already. And improve convergence because now there are no secondary groups. And accurate gradients, irregular mesh, and higher order inviscous property. These are being demonstrated in these papers.
You have a proof that the whole system becomes hyperbolic? It's only the diffusion part becomes hyperbolic, and then the Euler, right? Not the whole system.
I don't have it. No. So here's the probe. When we apply this to a boundary layer probe, we immediately see this problem. The implicit solver diverges, even though the linear relaxation converges very quickly. And even if it converges, the numerical solution is far from exact. Something's really wrong. And this is a serious problem for practical viscous flow application. Because viscous boundary layer is one of the major reasons why we want to do viscous simulations. But there are no problems in invisible limits. So this is a problem particularly for boundary layer. And yes, just increase. And I'll show you in the classical finite difference. This is a finite central difference for advection and diffusion in 1D advection diffusion equation. And this is, has a well-known mesh Reynolds-Number restriction. Mesh Reynolds-Number must be less than 2. This condition can be derived in various ways. You can use modal analysis and look at the oscillations. You can look at the diagonal dominance of the system. But there is another way to look at this. You can write this viscous 3-point finite difference scheme into this. The central scheme for advection is simply the average. But this dissipation term, it comes from this diffusion scheme. And we have mesh Reynolds number in the denominator. So unless mesh Reynolds number is small, if it's huge, then you lose this high frequency damping property. So a typical remedy is to use dissipated advection scheme. If you use upwind flux here, it's going to introduce a big dissipation. So that will help. But the problem is in the diffusion. But this simple fix doesn't work for hyperbolic scheme. In hyperbolic scheme, 1D advection diffusion is written in a system form. And here's the relaxation time. That's some length scale squared divided by the diffusion coefficient. And the length scale has been derived to optimize the fast convergence towards steady state for diffusion. That's one of the two. We call it a diffusion length scale. So we specifically denote it by LD. And if you look at this, finite volume upwind flux is very typical approach. And this spatial matrix Q can be constructed by looking at the eigenvalues and eigenvectors here. But this approach doesn't extend to compressible Navier-Stokes. I still cannot find it. And in one dimension, there is a proof that whole hyperbolic Navier-Stokes system is actually hyperbolic, but they also cannot find eigenvalues and eigenvectors. So the simplified approach was proposed in 2011. This is just a dissipation coefficient. So let's define this just separately. For advection, we use first upwind flux, and then for diffusion, I use outwind flux. But hyperbolic diffusion system is so simple that this absolute Jacobian becomes almost like a scalar. But this simplified approach is the problem. When we apply this to 3D Navier-Stokes, and then convergence probe was encountered for boundary interval. Extra dissipation from advection scheme will add extra dissipation only in the first equation. It doesn't do anything to the second equation. That's a big problem. And there are some fixes proposed by Dr. Nakashima Credo and Professor Badi, University of Strasbourg in France. They pointed out that the length scale needs to be reduced for High-Reynolds-Number boundary. And that way they were able to make it work. And that's a good approach because it's a simple fix. You just modify the length scale. But my questions remains with how much to reduce and what does it mean? And this was a very difficult problem. I spent a long time to approach this problem. But we found one that works for us. The approach is to forget the dissipation. You look for something else, and you come back to the dissipation. So we consider balanced high-order High-Reynolds-Number limits. It's important that if this diffusion term is negligible, it's just an advection problem. It's easy. But in this highly stretched boundary layer, these two terms the second, this coefficient is extremely small, but the second derivative is huge. And there is exact solution. It's well known. But the point here is that this exact solution is a linear combination of the two modes. One is a constant mode, and the other one is exponential mode. And this Rex is the Reynolds number based on this distance. This is an example of a Reynolds number 100 million. We want to be able to compute this solution. So the classical mode analysis, you assume certain form of the numerical solution. In this case, Uj, Greek for J, is some amplitude U times some mode C to the power of J. You substitute this solution mode into the, in this case, we substitute this into first order scheme, hyperbolic scheme, and then obtain this linear system. So for this linear system to have non-trivial solution, the determinant of this M should be 0. That's how we determine these modes. And there are 3 roots to this cubic equation.
You substitute to linearized equations, right? So not to non-linear equations.
This is a 1D linear advection.
Okay, linear.
Yeah.
I'm joking.
So there are a bunch of Reynolds numbers. This is a global A over nu. And this is a relaxation Reynolds number based on the length scale of the diffuse hyperbolic system. And this LD is 1 over 2 pi. And then mesh Reynolds number. And by looking at this, fortunately I was able to expand these expressions and then identify 2 modes. One is C1 is 1. This is easy to identify. The other one, the exponential one, comes from C2. C3 is less than 1, and it will be strongly damped. So by looking at C2, I think I was lucky. I was able to expand this C2 into this form. So it's clearly indicates that this is the exponential mode. But as soon as I look at this is the first order error of this scheme. And then looking at this coefficient, this fraction here, that's a big problem. Because for High-Reynolds-Number, this Reynolds number based on LR, if this is 1 over 2 pi, this gets huge, 1,100,000,000. And there is a square in the numerator, so this goes up unbounded. So that's explained here. Reynolds number infinite, and if L is 1 over 2 pi, this goes to infinite. So here's the plot of this first order error coefficient. And this is the relaxation ring scheme. If this goes to infinity, this actually increases unboundedly. Okay. And it cannot be too small too. But by looking at this plot, you notice that there is a minimum. And it is straightforward calculus to find this minimum value. You take a derivative and set it to be 0, and you solve it for the Reynolds number, that's 1. So this is actually 1. And which means, because Reynolds number LR is RE times LR, length scale should be 1 over Reynolds number to minimize the error. So this kind of answers my question. Why do I have to reduce this? To minimize the first order error. And how do I reduce this? Inversely proportional to the Reynolds number. And then look at the dissipation. If L is 1 over 2 pi, this AB, that this diffusion wave speed, is nu over L, which goes to 0 if Reynolds number goes to infinity. And we lose everything here. But if L is 1 over Reynolds number, and then the diffusion wave speed becomes equal to the advection wave speed, and it remains finite for any Reynolds number. So we retain this second dissipation for the hyperbolic diffusion system. So once I found this, if you look at this diffusion wave speed, it's a kind of easy guess, but looking at the error minimization, I think that's more convincing. And I have to check the iterative convergence because it was divergent. So I look at the implicit solver for second order scheme. So the right hand side is now second order accurate scheme, and the left hand side is based on first order Jacobi in 1 dimension. So it's easy to analyze. And then substitute Fourier component and look at the eigenvalue. This should be less than 1 for convergence. And on the left, this is we obtained with length scale 1 over 2 pi, the by choice. The vertical axis is Reynolds number, and the horizontal axis is mesh Reynolds number. So the red line corresponds to grid 0.1000, which is still not enough for 100 million mesh probe. So the mesh Reynolds number of about unit over 1, and here you have all 1. It doesn't converge. This analysis doesn't take into account boundary condition, but if it doesn't work in this way, with boundary, maybe with a better boundary condition, maybe. But as soon as you choose this length scale 1 over Reynolds number, this convergence rate drops about 0.5 all regions. So I expect this to be a good solution. So the greatest tip actually works. So if you increase, in this case, add more dissipation by taking L equals 1 over Reynolds number. But that was a first order scheme. We have to look at the second order scheme. The linear reconstruction to the face, the left solution and right solution. This U is a vector containing U and T, the gradient. And at the face, you have left and right states. But in order to do this, you need to compute the gradient, derivative at each data point. And there are a couple of options to do here. The scheme 1 is just apply linear least gradient for all variables U and P. In one dimension, it looks like this. And scheme 1Q, which stands for quadratic, is proposed for Navier-Stokes 3. But for the solution variable, because P is the gradient, when you do the least square, you can add curvature term. So in order to perform quadratic least squares within the linear least square stencil. So the coefficients are exactly the same as this linear least square, but because it has quadratic correction, this gradient is exact for quadratic functions. And this is very important because in no-centered scheme, if you have second order gradient, you can achieve third order accuracy. And there is another option, scheme 2. This is a natural option because P is gradient. Just use P as a gradient. And this one still have some issues. Details are in the paper. But in the 3D finite HNS in class 3D, we are using this technique. And second order scheme requires some little fix. But the analysis is so complicated. I was able to obtain some expression by doing a lot of simplifications. But this is still complicated. The best I could do was just to minimize the number of negative roots, the oscillatory modes for second order scheme, and then derive this condition. This means if you have an under-resolved mesh, the 1 over Reynolds number may not be the best choice. So the length scale will be increased a little bit. So okay. I thought some slides. Okay. Before I talk about Navier-Stokes, looks like I have 1D results here. So Reynolds number 1 million. This is a 1D case, linear average diffusion. Before this hyperbolic solver was diverging with 1 over 2 pi. But as soon as we use 1 over Reynolds number, it rapidly goes down. And the solutions are very accurate for this highly stretched case. So the mesh is actually, it goes, I think, more. But this is the maximum 10 to the minus 7. And there are more results in the paper with strong and weak boundary conditions. Weak boundary conditions typically work better. And viscous burgers also in the paper. And we apply this scheme to problem in 2 dimensions. This is a 1D boundary layer in 2D triangular mesh. And this is a highly stretched mesh, Reynolds number 1 meter. And the scheme 1Q converges rapidly here. So this is 1/2 pi, it doesn't converge. And this solid triangular singles are scheme 1Q. And I compare this with the Galerkin scheme. For this 129 by 129 in this tiny
Hiro, is it stretched mesh or just high aspect ratio mesh? Because I don't see.
Oh, high aspect ratio. Yeah, there are no big spaces.
Right.
Yeah, everything is half. As we refine the mesh, finally, the scheme, hyperbolic scheme, converges with faster in computational time than Galerkin. So the viscous stiffness, the stiffness coming from the second derivatives, not well, it doesn't appear if the grid is too coarse. But as you refine the mesh, at some point, it will kick in.
Do you continue to get this kind of result if the mesh is in fact highly stretched? I can see you have high aspect ratio, but now if it's highly stretched as well, does that add any problems in terms of getting this result?
Problem? No, I don't expect any problem.
I'm sorry, I'm missing the high aspect ratio. I think I see more. Is it just
I look at the
Like vertical
Because,
scale is extremely
oh,
small.
okay.
It's
Not
not
just showing the
Fine, yeah.
Yeah.
This is,
and it's a uniform mesh in the other direction, though, right?
this is 2D.
Yeah, but
It appears to be uniform. That's why I point about it.
That's
It's
uniform.
stretched. It's not.
It's high aspect ratio, but uniform.
uniform in that direction.
Yeah. So this was the difficult problem. But when I look at the solution accuracy, the solution is second order here, even though advection scheme is third order. But like I said, advection and diffusion have both equally important. You don't get third order accuracy for boundary. And the Galerkin second order, and the gradient for hyperbolic is supposed to be same order of accuracy for the solution. So y derivative is second order, but x derivative is only first order accurate. This is another issue that I still don't understand. But that's typical for least square gradients. So, okay, yeah. But with Galerkin, the gradients are computed by least squares, and they are all first order. But if we look at this y derivative distribution, and if they both give very accurate results, the Galerkin or hyperbolic. But if you zoom in, you see this slight oscillation obtained by this viscous square. So the smooth gradient is a property of hyperbolic scheme, and it is confirmed for this problem. So the extension to hyperbolic Navier-Stokes. I like this length scale approach because it's simple and relatively easy to extend to Navier-Stokes. For hyperbolic Navier-Stokes, we have 3 different length scales. One for the density gradient and the other for the velocity gradient equation and heat fluxes. And we apply the same correction to all these lengths. So in this form, we introduce some switching function based on the Reynolds number. And LD is basically 1/2 pi. So this here is the one simple switching function. Basically what it does is for small Reynolds number, it gives 1/2 pi. And then for high Reynolds number, it behaves like 1/2 Reynolds number. And this minimum function is not smooth, but you can make it smooth. There's a formula in the paper. So the question we faced when we look at this extension was, okay, what Reynolds number should we use? One is a local Reynolds number using the local velocity and the local viscosity. So it's a function of the solution. Or the free stream Reynolds number, so it's constant everywhere. That's simple, but I'm not sure if it's going to work. And there is an interesting approximate function, 1/√ of the Reynolds number. And this is interesting because this is actually the first formula I obtained when I first encountered the problem using a different approach. And it was working fine for hyperbolic Navier-Stokes in 3D. But later, when I looked at the 1D absorption diffusion problem, I found that this doesn't work. But using somehow this second order correction, overall, this is a very good approximation, and it works very robust. And this is one of our favorite formulas at the moment. And then we tested these formulas for the laminar flat plate, Reynolds number 1 million. This is a pure tetrahedral mesh.
Okay, now you should say 1 million based on what?
Length of the flat plate.
Okay.
And the length is 1. So the input Reynolds number should be 1 million. Yeah, that's very important. And the results are, well, satisfactory, but it now converges. This compares with fast 3D, default fast 3D, and the 3 different options for the evaluation of the Reynolds number in the formula. There are 4 grids, and this is the finest grid convergence results. And for linear relaxation, we fix 15, CFL 200, and HN's Jacobian is completed by automatic relaxation. So we only show the iteration, but you can imagine that hyperbolic Navier-Stokes is currently more extensive. So the convergence history, interesting. They're very simple. There's some funny feature here, but it comes down. This is with this approximate form, 1/square root of the free stream rate. And we don't see any difference between the local evaluation and free stream evaluation of the Reynolds number. That's interesting.
It's maybe distraction, that's what. It looks like multiple solutions.
Okay, why did you show it on the same scale? In terms of the number of shadings.
Same scale?
The blue line or the blue line.
What do you mean?
I would mention possibility because they are both diagonals of the single processing. The double processing, so in some situation they have this spike before converting because of the single processing.
Oh, you have to first go to some solution before turning it on?
No, it's just this spike just because of my
You're looking at the whole history.
the whole factor. They go
Just
Oh,
like
the
it's
good,
a term
okay.
of minus
Yeah.
11 and a half, it goes crazy for a bit.
Yeah.
So it spikes up at that.
Yeah. So my question is, do you get the same solution at before spike and after you converge to the spike? So it's like solutions.
I have to
It's
see
just
this.
what we were talking about from the other day, when
Over
we were
the
saying, oh, you have to be more exact.
Yeah.
When it's more
Okay,
exact, it's
I'm sorry to bring him. It's
No, I think that's important, but I will show the drag coefficient. Yeah. So this is compared with the Brazil solution. This is Mach 0.3. And here's the drag coefficient convergence over H/D, where H/D means the effective mesh space means computed based on the number of equations. So 5 equations or 20 equations. So otherwise it's not fair. So along each vertical plane, the number of discrete unknowns is the same. So this green is the fancy it converges to the Bradley's estimate of the drag coefficient. And hyperbolic schemes, they converge fast for the same number of discrete unknowns. And we don't see much difference, but 1/square root does a slightly better job. And when we look at the plot, the skin friction over flat plate, we found that this is very rare tetrahedral mesh. The fast 3D underestimate skin friction near the leading edge. Hyperbolic schemes overpredict, and it does a very good job further to the leading edge.
Hiro,
Yes.
tell me again, what is this degree of freedom? Is just number of nodes, or it accounts for the fact that in hyperbolic Navier-Stokes there are
Square
no
root
equations?
of do you remember the
Number of independent variables too?
the number of those square roots.
and times the number of variables you have.
Number of
So it accounts that
It
so
accounts
you
for
have
the
20 equations.
variables.
Yes.
Okay.
That's why we are using the same grid, but like this closest one has more much smaller edge.
Okay.
Yeah, because we have more value.
Okay, so that was
Yeah.
it's just amazing that they some of them almost match. Not all of them, but
Yeah. Some of them, blue ones. Not
yeah, I mean,
here.
fancy again, I would expect much wider shift kind of between vertical lines, but last one is definitely shift.
Okay, so you ran full 3D on a much finer mesh than the HNS one.
No, they have the same
Same
mesh.
grid.
The same mesh. The points are the same mesh.
This
Right,
this
you
grid
are-
and this grid is the same.
Square root number of mesh times number of variables, which, okay, I gotta think about that for a minute.
Actually, I said
Okay.
But is that fair to you? Because when you have the HNS, so you're got a first order system, whereas the quantity is the second order system. So in terms of work, is that fair? I mean, I know you increase the number of independent variables, but you have first order system.
Yeah, but here, when you look at the residual equation or linearized system, number of unknowns are the same along this track. That's how I wanted to look at it. So now you have same number of discrete points, and you apply similar algorithms. And computing time still slightly higher because you have 20 by 20 Jacobian plot.
Yeah, I was looking at it backwards. Yeah, no,
Oh,
makes sense. Thanks.
Yeah, we can discuss more. This is a conclusion. So 1 over Reynolds-Number for High-Reynolds-Number boundary layer flows improves accuracy and iterative convergence. This station is retained, which vanishes outwards. And may be validated for appreciation. That's a good news. For now, it's what. And even the 1 over square root, a simple approximation works great. So HNS can be made useful for accurate and efficient boundary layer calculations. The most important application that we are looking at is, of course, the cavernous. Cavernous is a High-Reynolds-Number applications, and there are boundary layers. So this problem had to be overcome. So now we are trying to move on to rounds and try some of the cavernous model resource website. In this case, chemistry cylinder and OM6. But issues still, of course, remain for this scheme too. Details in the paper. The problems with irregular stretch grids and 3D viscous spaces. For 3D, so far it doesn't work at all. And accuracy deterioration, this is not a serious problem. It still gives lower error, but at the conventional scheme. But I'd like to understand why I'm losing one order in that direction. Or if I refine enough, I may recover the design order accuracy. But in any case, I'm not very worried about this problem too much because we have the greatest difference. So keep adding this station until it works. Thank you.